Part A asks for the total charge on the rod. To find this, you would just multiply the linear charge density times the linear length. The linear charge density is given to you as lambda. So, to find the linear length of the rod, you would find the portion of, well, you can see that is a portion of a circle. It's given as 60 degrees up and 60 degrees down. That's the same thing as 2 pi over 3 radians, which is equal to 120 degrees. So then, arc length is equal to r theta, with theta in radians. So to find the arc length, or the linear length of the rod, you would multiply 0.1 times 2 pi over 3. And then finally multiply it by the linear charge density, which is given 1.5 times 10 to the negative 5. And from this you get 3.1 times 10 to the negative 6 coulombs. And that's your final answer for part A. Part B asks you to find the magnitude and direction of the electric field at the center O of the arc. Since the arc is entirely positive charge, the electric field is to the right, since the center O is to the right of the arc. All of the y components of the electric field, however, cancel out, leaving a positive x direction for the direction of the electric field. Finding the magnitude of the electric field, you would need to find the differentials of the electric field and add them up, since each part of the electric field is in the x direction is different, because you need to take into account the direction. So dE equals k dq over r squared cosine theta. Cosine theta because cosine theta equals adjacent over hypotenuse, and you're trying to find the x direction, x component of the electric field. So your variables in the right side of the equation are not the same, so you need to get them onto the same variables. To do this, you use an old relationship that you got from part A. Q equals r theta lambda. R and lambda, however, are both constants, so when you take the derivative of this, dq equals r lambda d theta, and you can substitute this back into your differential equation. So dE equals k r lambda cosine theta over r squared d theta. So from here, to find E, you would integrate both sides. Integral of dE equals E. The limits of the integration for d theta, well, is 0 to E. Limits of integration for d theta, however, are negative 60 degrees to 60 degrees, or radians would work too if you'd like. K r lambda over r squared are all constants, with one r cancelling out. So E equals k lambda over r. Integral of cosine theta is sine theta. So sine theta from negative 60 to positive 60 degrees. And once you plug and chug all of that to get your numbers, E turns out to be equal to 2.3 e to the 6 newtons per coulomb. And that's it for part B. For part C, you look at your equation sheet and see the equation potential equals KQ over R. However, you have to sum up all the differential V's. So dV equals K dQ over R. This time, however, there is no cosine or sine or any trig because potential is a scalar quantity. So you don't have to worry about the y and x components. So if you just integrate it from 0 to V, 0 to Q, since K and R are both constants, you just get your equation V equals KQ over R. If you plug in all of this, with Q being your answer from part A, you get V equals 2.8 times 10 to the 5th volts. Part D asks you to determine the magnitude and direction of the force that must be applied in order to keep the proton at rest if it's placed in the center O. This would be a force to counteract the electrostatic force produced by the positive charge on the rod. So from part B, you're ready to determine the electric field. So from your handy dandy equation sheet, you can see E equals F over Q. Solving for F leads you to F equals QE. So then the Q would be equal to the charge on a proton, which is equal to 1.6 times 10 to the negative 19 coulombs. And E would be your answer from part B. So plugging in both of these, you would get an answer of 3.7 times 10 to the negative 13 newtons. And this force would be to counteract the electrostatic force, so it would be in the negative x direction. And that's it for part D. Part E just asks for a description of the motion of the proton if it's released. This would just be accelerating to the right, but with a decreasing acceleration. This is because of the electrostatic force created between the proton and the positive charge on the rod. However, because of Coulomb's law, this acceleration decreases because F equals KQQ over R squared. As the distance increases, the force decreases. Since F equals ma, if the force decreases, acceleration decreases. On a side note, while I did not show much of the plugging and chugging of numbers, you should show plugging in plugging in numbers for these kind of problems, because they may give an extra point or two. Good luck on those FAQs.